Alright, what we're looking at right now is how to graph a reciprocal function. So we need to know a couple things about each function and how it works. So when we graph a reciprocal function, we have a parent function here of 1 over x. So when we're graphing, we want to look at what's called a vertical asymptote and a horizontal asymptote. So a vertical asymptote is a line that is approached by the function that the function never touches. So this line, this curve, will approach this green vertical asymptote but never touch it. It gets infinitely close, never touches. So we have a domain of all x's except 0. So that's what this says right here. Okay. All x's except 0. And then the range, this is a horizontal asymptote here at 0. This red line. So again, we're approaching this red asymptote here. We're getting closer and closer, but never touching it. So we have a range of all y's except 0. So that's an asymptote. So those are going to become very important in math. So let's take a look at example 1. So how do we tell by just looking at a function without graphing it what the asymptotes would be? So determine the value of x for which the function is not defined. We took a look at this before when we were looking at when we were solving rational equations. We looked at what would cause the denominator to be 0. So if we look at this function, we just look at the bottom and we say that the denominator cannot equal 0 because we know we cannot divide by 0. Okay, this is the thought process that we had when we were looking at rational equations when we were solving. So if we solve for x here, we would say that x cannot equal 5 halves. Okay. So go ahead and try these. Go ahead and pause. So in this first one here, we would say that x cannot equal 1. We know that if we plug 1 into the bottom, that would be a 0. And in this one, we would say x cannot equal a negative 2/3. Because if we set that equal or not equal to 0 and solve for x, we would subtract 2 divided by 3. That's what we would say. So example 2, taking this a little bit further, so we're identifying asymptotes, so that's that new term. That's the lines that are not touched by the curve, by the function. We're stating the domain and the range of the function. So if we look at the equation or the graph, we should be able to tell what our vertical asymptote would be. Our vertical asymptote is that line, that x value that cannot be touched. So the x value that we cannot have. So we would say the vertical asymptote is at x equals 1. So this dotted line here is x equals 1. We know x equals a constant, that's a vertical line. Okay. Horizontal asymptote. So horizontal asymptote would be anything that would be added on or subtracted at the end of the function. Okay. So right now we have a plus 0. So the horizontal asymptote would be y equals 0. Okay, and if we look at the graph, y equals 0 is the x-axis. That's our horizontal asymptote. Domain and range. So domain and range, we looked up here when we looked at domain. This is a different way of writing it, so we're going to try this. Alright. So domain is dealing with x values, so we can say that all x's such that x does not equal 1. So that's just a different way of writing. We could use our other notation that we learned earlier in the year. And same with the y's. All y's such that y does not equal 0. And that's it. Let's try the next one. So vertical asymptote. Vertical asymptote dealing with x's. What can x not equal? X could not equal -1, so that's what our vertical asymptote would be. Horizontal asymptote. Remember, anything added on or subtracted on the outside, the end of the function would be our horizontal asymptote. So we're at y equals 2. So domain is all x's such that x does not equal -1. And then our domain would be all y's such that y does not equal 2. Alright, let's take a look at the next step here. Well, we got a checkpoint. So checkpoint, go ahead and pause there and try that. So vertical asymptote would be at -1, and horizontal asymptote would be at -3. Domain is all x's such that x does not equal -1, and the domain is, range would be all y's such that y does not equal -3. Alright. And again, if we graphed it and checked it, we would see that we're at -1 for the vertical asymptote and at -3 for the horizontal. So it's a good idea to probably graph it and just double check that we found our correct answers. Alright, now we need to look at transformations of reciprocal functions. So it follows pretty much the same formatting that we've used for every other equation. It's just a little bit different looking at how the parent function would be set up. So we have an a value over x is the parent function, or 1 over x. So a number on top other than 1 would mean that it is getting vertically stretched or compressed. So we're looking at if it's bigger than 1, it's growing faster, so it's getting stretched. And if it's between 0 and 1, if it's a fraction, then we know we are compressing by that factor. The h value, that's the shift left or right, so the horizontal translation. And then the k value is shifting up or down, and that's going to be our vertical translation. If the a value is negative, that means we're reflecting over the x-axis. So it's all things that we've looked at before. It's just a little bit different of what we're looking at, or where these things are located in the function. So using the graph, the parent function, 1 over x, so describe the transformation that takes place. So if we look at the first one, what's different between the parent function and this function? Well, we have this subtraction of 3 in the denominator, so that's going to be this h value. So we're subtracting a 3, a positive 3, so we're going to shift right 3. So that's all we need. So right 3. Horizontal translation to the right by 3. This next one, what's different between these two? Well, the subtraction of 2 at the end, that is the k value. So we are going down 2. And then in this one we have two differences. So we have subtraction of 2 on the bottom and then plus 1 on the end here on the outside. So we're going to the right 2 and down, or no, up, sorry, plus 1 would be up 1. Alright, take a look here, write an equation to represent the new function. So we have a parent function is translated 4 units to the right, 3 units down, and reflected across the x-axis. So we know reflection over the x-axis, we can start there, would be just a negative 1 on top. Shifting right 4, we need to take away 4 from x, and we're going down 3 units, so that's on the end. We're going to subtract 3. Parent function's translated 7 units up, 1 unit left, and then vertically stretched by a factor of 2. So vertically stretched by a factor of 2, we're just going to multiply by 2 on the top. We're going left 1 unit, so we're going to add 1 to the x. So making sense of that, if we're shifting left 1 unit, our vertical asymptote is at 0 for the parent function, and we're going to go to negative 1 if we shift it to the left. And then up 7. Again, with that, we're at a y equals 0 for our parent function 1 over x. And we're going to shift that line. Everything gets shifted up by 7 units. So we're at plus 7, or y equals 7 for our horizontal asymptote. And then the last thing we got to do is put it all together and be able to graph the function. Okay? And it doesn't have to be anything pretty. But if we look at the parent function, our hyperbola here, we're up here we're in the top right first quadrant, and then we're in the third quadrant. So we need to remember that unless we flip over reflect over the x-axis, that's where we're going to be in the first and the third. So first we need state domain and range, and then we can graph it. Okay, so domain would be all, something crazy there, all x's such that x cannot equal negative 5. And the range would be all y's such that y cannot equal 3. So we have a vertical asymptote at negative 5, so 1, 2, 3, 4, 5. So we could go dotted line here. That's how we represent an asymptote. And then we have a horizontal at y equals 3. So 1, 2, 3. Here is our horizontal asymptote, and then we can just simply draw a curve here. Now, if we wanted to make it look a little bit better, we could plug in some x values into our function to find out what the y value would be. But we're just drawing a rough sketch here. And then we just draw one down here. Because if this were the origin, we were at the origin for the parent function, now we're here. We just think about the first and third quadrants. So top right, bottom left. Let's go ahead and try these real quick. Pause the video. Domain would be all x's such that x cannot equal 1. And range all y's such that y cannot equal 2. Okay, so we have x equals 1 for vertical and y equals 2 for our horizontal. Alright, so now what we need to do is remember that we have a negative 2 here, so we're vertically stretching by 2, and we have a negative, so we're reflecting over the x-axis. So instead of top right, bottom left, we are top left, bottom right, and we're growing a little bit steeper, a little bit quicker. But it's going to be kind of hard to show unless we take x values and plug them in to find out what the actual y's are. So again, we're just rough sketch here. Right? The big idea here is that we're reflecting and where are our asymptotes. And then here we would have x cannot equal 3. And y cannot equal, oops, I meant to have cannot equal 4. And let's see, 4, 2. So vertical, horizontal, vertical would be 1, 2, 3. And we have a positive 1, so we know we're just standard here, top right, bottom left. Okay, that's it. So let me know if you guys have any questions about this. We can go over this. I want to get a lot of practice in on this. This is a huge thing for calculus and any kind of higher mathematics. So just make sure we have this down. And that's it.